Hello class, we are now on section 2.1, angles and their measure. So today what I'm going to demonstrate are a few things, but the first thing that I'm going to start off with is drawing an angle. And so whenever we're drawing angles, the first thing that we need to do is we need to start off with a ray, and that ray starts with the vertex. That is the vertex, and this on an angle is called the initial side, and then we produce our other ray. This here is called the terminal side, and the angle that's produced is always going to go counterclockwise. And this angle here is 45 degrees. We could use a compass to measure it, but I know it's 45 degrees because that ray, the terminal side ray, is y equals x, which is along the 45 degree side. So this angle would have been 45 degrees. If I draw a negative 90 degrees, so again we start with the vertex, and we're going to have our initial side, and then our terminal side. Since we're going at negative 90 degrees, we're going in this direction. We end up with a negative 90 degrees, and we see that a negative 90 degrees is a right angle. But again, the way that we do the angles is it's always going to be, for positive, is going to be counterclockwise. So angles are always positive going counterclockwise. So if you go clockwise, you're going to end up with negative degrees. Okay. Let me just draw one more for you. If I had 405 degrees, we have our vertex with our initial side, and then what's going to end up happening is we're going to go a full 360, and then we need to go, let me erase that, sorry. We're going to go a full 360 and then an extra 45. So that's going to produce this angle. One full rotation is 360 degrees, plus the 45 degrees beyond the initial side will give us 405 degree angle. So that's how you draw angles. Just a couple of examples for you guys to be able to do that. The next thing that I want to talk about is converting between decimals and degrees, minutes, seconds measures for angles. And so the way that the book explains it is it gives you this counterclockwise revolution is 360 degrees, and it says that 1 degree is equal to 60 minutes, and that 1 minute is 60 seconds. But I'd rather have it in a way that you'll be able to understand a little bit clearer. So the way that I am going to demonstrate it to you guys is this. It's 1 degree. They have is 60, is 60 minutes, but I'd rather you see it this way. 1 minute is 1/60th of a degree, and if we do the seconds, the way I'd like you to see it is, if we did the ratio, it would look like this. But again, I'd want you to see it as 1/60 minutes is 1 second. But that can even be cleaned up, and so we can see it as 160 times 160, and instead of being a minute, we're going to change it to degrees. And then that 1 second is the same as 1 over 3,600 degrees. And that's important because those are the measures that we're going to use to do conversions. It's these guys. So these are the ones you really want to know. So in doing this conversion problem, 50 degrees is not going to change, but we're going to write it in terms of sums. So we're going to go 6 minutes plus 21 seconds. And then I'm going to break that up further to go 50 degrees plus 6 times 1 minute plus 21 times 1 second. And you'll see what's going to end up happening here is I'm going to go 6 times, and I'm going to use this ratio here. So I'm going to go 1 over 60 degrees, because what we're trying to get to is degrees. I want everything in terms of degrees. And then 1 times 1 second, we know to be 1 over 3,600 degrees. Pulling out our calculator, we see that we're going to get 0.1 degrees plus 0.0058 degrees, which will result in 50.1058 degrees, and this is our answer. So the important piece is to use these blue highlighted pieces that I used for a minute and for seconds. The critical piece is this is being substituted by the blue and this is being substituted by the blue accordingly. For this one for seconds and this one for minutes. Okay, let me try to do a conversion the other way so you guys can see that also. So what if I have degrees and I want to turn it into degrees, minutes, seconds? What we're going to do is we're going to break it up precisely like we did before. So I'm going to go 21 degrees plus 0.256 degrees. And then I want to change that degrees, that 0.256, to times 1 degree. But from the earlier information that we had, we can see that 1 degree is the same as 60 minutes. And then when we multiply that, we're going to get 21 degrees plus 15.36 minutes. But we don't want decimals for minutes, so we're going to convert that and get 21 plus 15 minutes plus 0.36 times 60. Well, let me actually show it so you guys can see. Times the 1 minute, and then that's going to be 21 degrees plus 15 minutes plus 0.36 times 60 seconds. And when we multiply that, we're going to get 21.6 seconds. And now we can combine this so it's written in the correct form. We're going to get 21 degrees, 15 minutes, and we're going to round this up to 22 seconds because we want it to be in just seconds. And so our answer is this piece here. But again, the conversion, we have to remember that 1 degree is 60 minutes and that 1 minute is 60 seconds. And that's what I used for the conversions that I used here. If you need additional help with this, please go ahead and message me and I can do further examples for you guys. That's not a problem at all. All right. To find arc length, we have a formula. And the formula says that for a circle of radius r, a central angle of degree radians, theta degrees, subtends an arc whose length is s. Now, the important thing to understand is what a radian is. So a radian is the angle that's created when the radius is the same as the arc length. So in this case, you see how this is a 3 and this is a 3. These are the same. The degree that's produced here is 1 radian. In this example that they have, this is a length of r. The arc length is a length of r, and so the degree there is a radian. That's something that's important and you should know. It doesn't matter how big the circle gets. Because it's proportional, the angle is going to end up being the same. But that is a radian. So using this formula, I'm going to solve this example here. So we know that the radius here is 2 meters. And we know that the angle, our theta, is going to be 0.25 radians. Now, the formula tells us that the length, the arc length, is equal to the radius times our angle. So S is going to be equal to 2 meters times 0.25. We don't write the radians. We don't need to write those units, and so we are going to end up with 0.5 meters for our arc length. So this is the arc length, provided that we have a radius of 2 meters with a central angle of 0.25 radians. The important piece is please remember that formula. It's important and it will be useful. Okay. To convert from degrees to radians and to convert from radians to degrees, what we're going to use is this ratio here. This is the most important piece, is that number 7. So since I want to go from degrees to radians, I'm going to want to have pi in the numerator. So let me do example A. 60 degrees times this ratio. Since I want radians, I want pi in the numerator, and I want the 180 degrees in the denominator. Now, 60 divided by 180 is going to be a 3, and we're going to have pi over 3 as our solution. For the second example, if we had 150 degrees, again, since we want radians, we're going to multiply by pi over 180. And this is going to be, and I'll show the step just so you guys can see it. This is degrees, over 180 degrees. We can see that this is going to clean up also, and it's going to clean up to be 5 pi over 6. When you see pi in the numerator, that's in terms of radian. If we're eliminating pi, we're going back to degrees. So let me show that for you so you guys can see this. So here I'm trying to get degrees. So now the ratios that we had was pi over 180, but since we want to get to degrees, we're going to go 180 over pi. So I'm going to have pi over 6 times 180 degrees over pi. We can see here that the pi is going to cancel, and then our math is going to produce 30 degrees. Now, for the next problem, it's actually a very good one. We see we have 5 radians. We want to go to degrees, so we're going to go 180 degrees over pi. That's going to multiply to be 900 degrees over pi. And then when we use our calculator to divide it, we see it's 286.48 degrees. It's almost a full revolution around our circle. Okay. To find the area of a sector, basically we're just what's covered, what's swept in the circle. So if I had a circle, and this is the radius covered, this piece that's shaded would be what we're looking for, and we see that as the area of the sector. So that would be the area of the sector there. So in the example that I gave you, we have a radius of 2 feet with an angle of 30 degrees. But notice something in this problem. We're in degrees here, but our formula is in terms of radian, so we need to convert that 30 degrees into radian before we can use it. So we're going to get 30 degrees, and since we want, again, radian, we need to go pi over 180 degrees. And that's going to result in pi over 6 as the theta that we're going to use. So now from there, using the formula, area is 1/2 r squared theta. We're going to get area is equal to 1/2 2 feet squared times pi over 6. That's going to result in the area being pi over 3. I'll show the steps so you guys can see this. It's going to be 1/2 4 feet squared times pi over 6. And that's going to result in the area being pi over 3 feet squared. And it should make sense that it's feet squared because we're talking about an area. And so area is in terms of squared units. And so the result is going to be 1.05 feet squared. Right there's your answer. Okay. So there's a couple of formulas here. The formula that we already know is that this number 9 one here, that velocity is equal to the distance divided by time. That's a linear speed. Angular speed uses omega, that weird looking W, and it's the angle divided by the time. And again, the angle is measured in radians, so be careful. If I give you degrees, you need to be able to convert that. Now, our angular or our linear velocity in terms of using omega is going to be this one. V is equal to the radius times omega. So let's do an example with this so you guys can see. All right, so I have a child spinning a rock at the end of a 2-foot rope at a rate of 180 revolutions per minute. Find the linear speed of the rock when it is released. So he's going to launch this thing. So in order to be able to find the omega is going to be found by doing 180 revolutions per minute. And then we're going to multiply that, because we need to be in radians, times 2 pi, which is a full circle, radians over revolutions. And that's going to equal 360 pi radians per minute. So that's the number of rotations that is occurring per minute, the angle that's being created. So to get that linear velocity, it's going to be, again, the velocity is equal to the radius times the omega. And that's going to be 2 feet is the radius. So we'll go 2 feet times 360 pi radians per minute. That's going to result in 720 times pi feet per minute, which results in 2,262 feet per minute. So pretty fast. When this child lets this go, this could hurt somebody. I hope this has been beneficial. Again, if you have any questions, please feel free to email me and I can post them in the discussion area. Have a great day. Take care. Bye-bye.